Hello, this is Mr. Gilmore with the 9.6, the secant tangent angle theorems. We're going to introduce a new line today called a secant. And what we're going to see is that there's going to be some intersections formed by secant lines and tangent lines. And those intersections are going to form angles. We're going to be investigating those angles today and actually looking at, are there ways to find the measure of those angles that are formed as these secants and these tangents begin their intersections with our circles. So let's start with our definition of a secant. A secant is a line, a ray, or a segment which intersects our circle at precisely 2 points. So in other words, chords, which remember chords are these segments we've introduced since the beginning of chapter 9, chords are really just secants. If we extend those chords out, we form a secant line. In our diagram below, we're illustrating just a simple example of a secant line. We have circle A, such that line N is intersecting that circle at 2 points. And what we're going to see today with secants and tangents is that secants and tangents can actually intersect in 5 different ways. We can have secants intersecting other secants, and we can also have secants intersecting tangents, and we can also have tangents intersecting tangents. Now recall a tangent, remember, is a line that intersects our circle at precisely 1 point. Now, I found it that we're going to need to actually give a few other definitions before moving into these intersections of secants and tangents. The first definition we need to give is this definition we call vertical twin. So, for example, if you've named a pair of vertical angles, then what I want to do is if I pick or if I'm referring to one of those vertical angles, I want to be able to refer to the other member of that pair of vertical angles, and I'm going to refer to it as the vertical twin. So in our example below, we've got a pair of vertical angles, angle 1 and angle 2. I can, if I'm referring to the member of angle 1, but at the same time also want to refer to angle 2, I could say angle 1 and its vertical twin, which then is referring to angle 2. So angle 2 is really angle 1's vertical twin, and vice versa. I could say angle 1 is really angle 2's vertical twin. You'll see that I'll make use of this jargon in our conditionals when we talk about secant and tangent intersections. The other pair of definitions that I want to give are going to be related to where the intersections of our secants and tangents intersect. So where these intersections can end up, we can find that secants, secant tangents, and tangents can intersect on the outside of our circle, which means where that angle is formed on the outside, we're going to have a pair of arcs. One that's we're going to refer to as the far side arc, and the other refers to a near side arc. In the example below, this should illustrate this jargon of what is a far side arc and what's considered a near side arc. Because we're actually in the diagram below, we have this point A, which is the intersection of two secants, and it's on the outside of our circle. We find that that angle A, with its relative position, is closer to one of the two arcs that it's cutting. It's actually closest to this arc DE, which we're going to refer to that arc as the near side arc. It's the one that's closest to where the formation of angle A is. But then we also have this arc formed on the other side of our circle here, this arc BC, and we'll refer to that one as the far side arc because it's the one that is farthest away from our formation of angle A. And so you'll see that jargon, near side and far side, be used in our conditionals as we progress through the possibilities of intersections of secants and tangents. So let's take a look at the very first possibility of the intersection of secants and tangents. This first one is where we have two secants meeting or intersecting. And the first possibility of where these two secants can actually intersect would be on the inside of our circle. So in our diagram below, we're given two chords, which remember chords are just really secants. So these two secants, A, B, and C, D, that are meeting at point E. Now here's what we're going to prove. In this case, with our intersection of the two secants on the inside, each angle that's formed at that intersection is then half the sum. So follow along with me. It's half the sum of the arcs cut by it and its vertical twin. Because the intersection of those two secants form a pair of, actually two pairs of vertical angles, if I refer to any one of those angles, I also need to refer to its vertical twin, because its vertical twin also cuts out an arc. And those two arcs where the angle itself is cutting and its vertical twin is cutting are both involved in the conditional, or both in the sum that you're going to find to actually calculate the measure of that angle form. So in the diagram below, we're going to refer to specifically angle AEC. That's going to be the angle of our choice. We're going to prove that angle AEC is really half the sum of arcs AC and BC. So now why AC? Well, it's pretty obvious that AC is the arc that's being cut by our angle AEC. But then why BD? Well, because AEC has a vertical twin, and that vertical twin also is cutting an arc, which happens to be that arc BD. Now, if we were to put this into our symbolism, here's what we're going to prove. We're going to prove that the measure of angle AEC is really equal to half the sum of the measure of arc AC and the measure of arc BD. That's what we're going to prove, and we'll see the proof of this on the next slide. So again, this is the first possibility where two secants intersect on the inside of our circle. So here's our proof. We're going to prove that that angle AEC is half the sum of the arcs AC and BD, which means really we find it's half the sum of the arc it cuts and its vertical twin, right? The arc cut by itself and its vertical twin. So let's take a look at the proof below. We're given that AB and CD are intersecting chords at point E, which are really just intersecting secants. We're going to connect points B to C. Okay, we're going to connect those points B to C. And what happens when we do that is we actually form two angles. We form this angle here, which is angle BCD, and this angle here, which is angle ABC. And what you notice is that those angles are inscribed angles. And so we're going to use the inscribed angle theorem right off the bat. By the inscribed angle theorem, we know the measure of that angle ABC is half the measure of the arc it's cutting, and that angle happens to be cutting arc AC. And we find that the other inscribed angle formed, angle BCD, is also cutting an arc, and by the inscribed angle theorem, we claim that the measure of that angle BCD is equal to half of the measure of the arc that it cuts, arc BD. Now, we have a relationship between those two inscribed angles and the angle that we're choosing here to find this relationship, that angle of angle AEC. As it turns out, angle AEC is an exterior angle to the triangle EBC, and its two remote angles are those two inscribed angles. And so it turns out the measure of our angle AEC is equal to the sum of those two remote angles, the measure of angle ABC plus the measure of angle BCD. Well, now by substitution, take those inscribed angles out and replace them with the half arc measures that we calculated. So we have now the measure of angle AEC is half the measure of arc AC plus half the measure of arc BD. And moreover, we can simply factor out that 1/2, and we end up then with the measure of our angle AEC is equal to half the sum of the arc it cuts and its vertical twin. And so there we have our statement we're looking for, that the measure of angle AEC is equal to 1/2 the sum of the measure of arc AC plus the measure of arc BD. So QED, we get that proof. So that's our first example, our first case where the two secants can intersect on the inside of our circle. So now let's take a look at the second possibility, and this is where we're going to find secants intersecting on the outside of our circle. So the point of intersection is going to be a point on the exterior of our circle. In the diagram below, we have secant BD and secant CE meeting at point A. And what the second possibility, what the conclusion we're going to reach with this possibility is that the angle formed here at angle A has a relationship with its far side arc that it cuts and the near side arc that it cuts. And here's what we're going to prove, that the measure of angle A is actually equal to half the difference of the far side arc and the near side arc. In other words, in our symbolism, we're going to find that the measure of angle A is equal to 1/2 times the measure of the far side arc minus the measure of the near side arc. And that's going to give us that measure of angle A. Now, I'm going to leave this second possibility for you guys to prove on your own, but I would like to leave you with a piece of advice. And here's your piece of advice. You're going to make a simple construction to begin with. You're simply going to connect point C to point D, and here's why. When you connect point C to point D, you actually form angle C here as an inscribed angle. That inscribed angle is cutting our arc there, DE. But when you connected C to D, there's a second angle that's also inscribed. It's this angle right here, angle BDC. And angle BDC is cutting the arc BC, which means there is already a relationship between those two inscribed angles that are formed to the two arcs of the far side arc and the near side arc related to angle A. But also, if you take a look at this angle here again, this angle BDC, that angle, if you notice, is an exterior angle to the triangle CDA, and that means that measure of that angle is equal to the sum of its two remote angles, which happens to involve angle C and angle A. So you're going to use that piece of information as well, that triangle exterior angle equality, to actually then relate those far side arcs, near side arc, to that measure of angle A. Let's look at our third possibility. The third possibility involves now an intersection of a secant and a tangent. So secants and tangents, remember, secants intersect a circle at 2 points. Tangents intersect a circle at precisely 1 point. So one of the possible intersections of a secant and a tangent is actually intersecting at the point of tangency, which is where our tangent line intersects our circle. In the diagram below, our tangent line BC is intersecting our circle at point B, which says then our secant, or really the chord AB, is intersecting at that point B. So AB is our secant, BC is our tangent. We are then going to find this unique relationship between the angle formed between them. What we're going to find is that this angle ABC, this angle right here, it actually cuts out an arc. The arc that's formed from point A through point D, over here back to point B, there's a relationship with that arc and the angle that's formed between our secant and tangent. And here's what we're going to prove, that the measure of that angle, ABC, is actually equal to half the measure of the arc that it cuts. So it's almost a sort of variation of our inscribed angle, except for the fact that that angle that's formed is not an inscribed angle. The inscribed angle needs its sides to be chords. We only have one side being a chord and the other side being a tangent line. Well, what that means is we will actually see the use of the inscribed angle theorem to actually help us prove this. And I walk you through the third case on the homework assignment. It's tricky, which means I do make it a guided proof. So I'm going to refer to that proof on the worksheet for you to then again, in helping you prove this third case, we're showing that the measure of that angle formed between our secant and tangent intersection at the point of tangency is half the measure of the arc it cuts. And again, it's tricky, which is why I've broken it up into a guided proof for you. Let's move on to take a look at our next possibility. The fourth possibility is where we have a secant and a tangent meeting at a point outside of our circle. So in our diagram below, we have our tangent line AD, so D is a point of tangency, and we have our secant line AC, which means it's intersecting our circle at 2 points, point B and point C. What we're going to find here is that relationship formed again with the angle between our two lines, the secant and tangent line. It's going to be this angle A. And we use the jargon that we've talked about of far side arc and near side arc. As you see that the measure of angle A, as we extend the sides out, it cuts out this arc DC, and it also cuts out this arc DB. And there is our far side arc and our near side arc. And what we're going to find is that the measure of our angle A is actually equal to half the difference of the measure of our far side arc, CD, minus the near side arc, BD. And that's what we're going to prove in our fourth example here. Now, here is a piece of advice that I'm going to give you, okay? You are going to use case number 3 to help you prove case number 4. Okay, so this is our fourth possibility. You are going to use the third case, right? The third case. So number 3, the third theorem on your worksheet, you're going to use that to help you prove this conditional here, prove that this is actually true, okay? That angle A really is half. And how we're going to use that is actually you're going to begin by doing a simple construction. And I believe I've actually mentioned the simple construction on the assignment, on the homework assignment. And that simple construction actually then involves forming a secant line uh, between two of our other points, such that you know then you're going to form then you're going to form a a relationship between the arcs that when we insert that secant line, it's going to form these arcs that are going to cut it. So really what you're going to do then, it's a very simple construction. All you're going to do then is you're going to connect point B to point D. Okay, point B to point D. And when you do that, you'll notice that angle CBD is actually an inscribed angle, right? This angle CBD is an inscribed angle. That inscribed angle is cutting out that arc CD, which means you know there's already a relationship between that angle and the arc it cuts. At the same time, this angle here is also a exterior angle again, which means you can use your triangle exterior angle theorem to relate it to your angle A, which happens to be one of its remotes, and this other angle right here, angle ADB. Now, this angle ADB is actually where you find the intersection of a secant line and a tangent. And that's where number 3 comes into play. Because that's what we proved in our case 3, where we have our intersection of a secant and our tangent at the point of tangency, which means the measure of our angle ADB is actually equal to half the measure of the arc it cuts, which happens to be our near side arc DB. So that's very simple construction, and the use of the case number 3 is going to help you prove case number 4. I'm going to leave that one for you guys to put the details together on your own. Now let's look at the 5th case of our intersections of secants and tangents. Now we've looked at secants intersecting secants and tangents intersecting secants, but there's actually this 5th case, which is our tangents intersecting another tangent. So we have point A as the intersection of these two tangents, BA and CA. And what we're going to prove again is that there's this angle formed A that's related to the far side arc that it cuts and the near side arc that it cuts. So its far side arc is this arc BDC. Oops. And the near side arc is this arc BC. Okay, and so what we're to find is the measure of our angle A, is equal to half the difference of the far side arc and near side arc, which is the measure of our arc BDC and the measure of our near side arc BC. So that is what we're going to prove, and I'm going to leave this one for you to do on your own, but I'm going to give you a piece of advice. What helps you prove this 5th case is actually case number 4. Why case number 4 is going to come in handy? Let me explain what you're going to do. You're going to take point A and you're going to connect it to point D. And what you form then is our case number 4, which is an intersection of a secant and a tangent on the exterior. So number 4 then actually helps you with this angle formed, angle BAD. You know a relationship already then about that angle BAD, and you have this second angle formed, angle CAD, and number 4 is going to help you also with that angle as well. And then the sum of those angles will add up to the whole angle A, which is going to lead you into forming your final conclusion here with the angle A is actually, again, we see this half in there, half the difference of the far side arc and the near side arc. So we've come to the end of our lesson with our secant tangent angle theorems, and you're going to want to make sure you hop over and take a look at that 9.6 worksheet. If you have any questions on any of the theorems that I left for you guys to prove on your own, please don't hesitate to email me and I'll get back to you. With that, be good and do good.